Welcome to the lecture 26 of Physics 10 in 30 lectures. In this lecture, we introduce the postulates of special relativity and look at its first application, relativity of simultaneity. We start this lecture with a chapter 13 overview, which briefly mentions all the topics that will be covered this week, between this lecture set and the next lecture set. The remaining lecture videos are borrowed Physics 4C lecture videos, introducing special relativity mostly conceptually. The first segment introduces the problem with the speed of light in the context of principle of relativity. Then the Michelson-Morley null experiment is described along with some numerical estimates. Postulates of special relativity lecture section restates the two postulates of special relativity and applies them to illustrate the fact that whether two spatially separated events are simultaneous depends on the reference frame. And the last couple lecture segments reinforce this idea with a couple examples, some with the use of spacetime diagrams. In the next lecture, we will look at the remainder of special relativistic effects. Now, we start with the chapter 13 overview. This is the chapter overview video for chapter 13, special relativity. By the way, when you look at this chapter, you will find that the sections are a little bit more mathematical than you are used to in this textbook. And the main reason is most of the textbook sections in our introduction to physics, it's curated from OpenStax College Physics. And I did that curating work, taking things that are more mathematical than is necessary in a conceptual physics class. And when I looked at their special relativity chapter, most of it seemed good. It was close enough. They didn't use any trigonometry, and the level of algebra that was there, it's maybe a little bit more than what we would use, but it was acceptable. So I used the entire special relativity chapter from OpenStax College Physics, just as it was. So that's how you will find the sections here, which is at the level of algebra-based physics. So they will appear a little bit more mathematical than you are used to. I will say, follow along what you can. And when you look at the homework, you will see that the level of math you need is what you are used to from our coverage of physics so far. So in this overview video, I'll just briefly talk about how these topics align with the sections. So special relativity, we start out with the postulate, Einstein's postulate of special relativity. Actually, the first postulate isn't really something that originates from Einstein. It's something that's very old, what we call principle of relativity. The laws of physics is same in all inertial reference frames. And Einstein's second postulate is one that's usually stated as saying speed of light c is constant. And you will see it in my lecture how this amounts to saying Maxwell was right when he put together his theory of electromagnetism. Only like 40, less than 50 years before Einstein. And out of these simple postulates, you get really counterintuitive effects. I think one of the most fundamental of these effects, and this is covered in section 13.3, is simultaneity. It's the fact that simultaneity is relative. And I look at it in the lecture from a few different angles, so I recommend you take a look at that. That it's not absolute, it's relative. It depends on what inertial reference frame you are in. This is again very counterintuitive, and people get confused about this all the time. If you are, not a problem. Even physics majors get confused. I would recommend you to look at the lecture videos, especially the ones using spacetime diagrams. And continuing to use Einstein's postulate, you can derive these relativistic effects called time dilation and length contraction. And I guess I would summarize this as time dilation. It says time passes slower. I would say moving clocks are slow because They are. If a clock is moving, the number of seconds they tick down, it will be slow compared to your clock, which is stationary. And in the lecture, you will see this derived. And length contraction says shortening of length along direction of motion, or the way I would phrase it is moving rulers are short. As in, if you have a meter stick that's moving relative to you and you measure its length, you will find that it's shorter than a meter. And again, because these are covered in detail in lectures, other than saying all these things, let me move on. And in relativistic mechanics, velocity addition, I don't think I covered that in any of the lectures specifically. It is covered in section 13.5, relativistic addition of velocities. And I'll just admit to something, which is that I hate that relative velocity addition formula. It looks so complicated. You do have a homework question on it, but within the homework question itself, you will be given the relativistic velocity addition formula. It's just a number sense question. And now about momentum and energy. I was looking at the homework questions, and it looks like I don't ask you any questions about relativistic momentum and energy. So if you want to treat these topics as optional, you can. You can also read about it in the textbook. Relativistic momentum is covered in section 13.6, relativistic momentum. And relativistic energy is covered in section 13.7, relativistic energy. So you can read about that there. And also I recorded a new lecture just going over relativistic momentum and energy. But you can consider that to be an optional material. You won't see any homework questions. And finally, the applications. I think I'll have to skip out on those. Other than to say, GPS, which is behind all the navigation stuff, GPS system wouldn't be functioning if in designing the system, they didn't take the relativistic effect into account. The clocks would go out of synchronization so quickly, except that we took the relativistic effects into account. The rest of it, you can read about it in the textbook. Nuclear fission and fusion, you will hear more about that next week as we cover nuclear and particle physics. Now, in the upcoming lectures, you will see Einstein's postulates, starting special relativity. It falls under the heading of principle of relativity. And it's not actually a new principle. Depending on your instructor, they might have even mentioned it in Physics 4a. And it's something you can actually reason through. What's the quickest way to do it? I can give you the scenario that Galileo thought up. There's this German phrase, Gedanken experiment, or I guess in English we call it thought experiment. And all it is trying to visualize or imagine a situation where you are trying to apply the laws of physics. So think of this thought experiment. You are in a submarine, and you are in your bunk bed, and in your room there's no windows outside anywhere. How would you know if the submarine is moving or not? Now, if it's a very bumpy ride, then you will know it's moving. Let's imagine that it's a very smooth ride. Or I guess most of us haven't been on submarine. Imagine you're on an airplane, and there's no turbulence, the windows are closed, so you can look outside. How would you be able to tell the difference between is the airplane flying versus is it just sitting on the runway with the engines running? Like, how would you be able to tell the difference? Can't really? How many here have been on an airplane? Yes. Once it's at the cruising altitude, have you walked around? Like, did it feel any different from regular walking around? Not really, right? Yeah, so that's our common experience. And that relates to what's called a principle of relativity. And I guess you could summarize it this way. Laws of physics are the same in all inertial reference frames. I think most people here are familiar with what reference frame is, coordinate system and all that stuff, right? The phrase that I know I skip in my Physics 4a is the phrase inertial. Can someone tell the class what inertial means?
It's from the Newton's first law.
I also skipped that. So Newton's first law defines inertial reference frame. Let's describe inertial reference frame without reference to Newton's laws. What's a synonym for inertial?
Homogeneous mass.
Not quite homogeneous.
Mass.
Mass? Oh, you're thinking of inertia.
Oh, inertial.
There's L.
Non-accelerating?
Non-accelerating, yeah, that's it. Inertial reference frame is a non-accelerating reference frame. It's quite simple. And in non-accelerating frame, Newton's first law applies. So this is the demo that you might use to illustrate it. So, we actually use this demo in physics 4a for independence of vertical and horizontal motion. And you could say, well, vertical and horizontal motion are independent because this is true. So the laws of physics are arranged in such a way that there's some spring-loaded mechanism here. And when I trip this thing, it launches a ball, right? And I could put this cart on in a different inertial reference frame. The inertial reference frame that's moving along with this cart. As long as I'm not pushing it, the frame that's moving with the cart, that's a non-accelerating frame. And so you have already seen how this ball moves in the reference frame of this room, right? And when I push it, you are going to see this ball moving in the reference frame of the room again. And this is what I'm asking you to visualize. Imagine you are an observer riding with a cart. How would you see the ball move? Would you see the ball move in a parabolic arc like this? Or you'll just see it moving up and down, right? So like, if you are sitting in an airplane and throw a ball up, then it just goes up and down back to your hand. But for someone looking at it from outside, it might do that parabolic thing. And in both cases, the ball returns to your hand because of this. Right? It's a fairly basic principle. In fact, it's kind of difficult to imagine this working in the nature working in any other way. Somehow that if you're moving, the laws of physics change, that would make physics actually very challenging. That would make science itself very challenging. So this is where I want to introduce a couple things that seemed to threaten this principle of relativity. Let me start out with the easy example. How fast does sound move?
331 meters per second.
Yeah, let me round it down to 340 meters per second. So speed of sound, let me write it down somewhere. So speed of sound, it's about 340 meters per second at room temperature, 1 atmosphere, et cetera, et cetera, et cetera. So if you could see the sound waves coming out of my mouth, you would see it moving at 340 meters per second. What if this source of sound was on a train? So let's say this is the source of sound, and the sound waves are going in either directions. If the train is stationary, then each of these wave fronts, as you look at it, it's moving at 340 meters per second. 340 meters per second, right? If the train is stationary. Now imagine that the train is moving at some, reasonable speed. Let's say that the train is moving at some speed of, what's a reasonable speed? 40 meters per second, that's like 80 miles per hour. So the train is moving at 40 meters per second. Like if you're standing out here looking at those sound waves, would they still move at 340 meters per second? No, it'll change, right? What does your intuition tell you? As you're observing it out here, what is the speed of sound from out here? Yeah, plus 40 meters per second. So from out here, you would see the wave speed of 380 meters per second for the sound wave that's moving in the same direction as the train. What about the sound wave that's going the other way? You'd be surprised. Like all this is very intuitive. That's why even, well, sorry, I don't mean to sound dismissive. That's why people could figure this out even before time of Newton, before there was laws of physics or something, I don't know. So this would be at 300 meters per second. And in fact, this leads to something called the Doppler effect that we could have covered when we were doing waves, but we kind of skipped. So these changes of speed of sound is what leads to Doppler effect. There are videos on YouTube where people record a fire engine passing by them. As it's coming towards you, the sound sounds at higher pitch, and it's moving away from you, it's at lower pitch. And it's tied to how speed of sound changes as the source is moving. Good? Now, does this fact, does that seem contradictory in any way with your sense of principle of relativity? Like the way you guys gave me these answers was intuitive. Principle of relativity is also intuitive, based on everyday intuition. Is there any disagreement between these two? Like, are you okay with the fact that speed of sound in this reference frame, 340 meters per second, and the speed of sound from where I stand are different? Yeah, it's all okay? Yeah, I guess, you know, the way you could, so let me slightly reorder this. So given that the laws of physics are the same, supposed to be the same in all reference frames, all inertial reference frames, what makes this inertial reference frame special compared to where I'm standing? That, you know, in this reference frame, you could say speed of sound is 340 no matter what direction it's going, but from where I'm standing, speed of sound changes depending on the direction. Like, what's special about that reference frame? It's moving at constant velocity. As it's moving, what else is moving at constant velocity with the train? Well, speed is not a thing. Well, wave is also not a thing, right? Because wave is the disturbance. I want an object that I can say is moving with it. That's that.
Whatever is making the sound.
Okay, the source. So this is something common with all waves, except for one, which we are getting to. The medium for the sound wave is moving along with it. So the medium for the sound wave here is air. And in fact, the number that Javier gave us is specific to the properties of air. If you make the air thinner, denser, then it'll change things. So this is the only reference frame where air is stationary on average. That's why the speed of sound didn't depend on the direction. From out here, the air itself is moving. So this speed of sound, what it is really, it's relative to air. That's why everything that we are describing here intuitively is all consistent. So you make the air move, then speed of sound will sort of add to that movement of air. And you could get the same thing if there's a wind blowing past. Wind will also just throw the sound waves off, of course. Good? Okay. So this is all good since so air, or I guess medium for sound wave. So most people didn't have problem with the principle of relativity. It fits with everyday experience. When you are describing things like waves, sound waves, then you can describe how it fits into the principle of relativity by saying that the speed of sound is relative to the medium that the wave is traveling in. So yeah, you make the special whatever. Up until late 19th century, well, late 19th, early 20th century, that's when physicists discovered one wave that does not appear to have a medium. There's one wave that you know of so far that doesn't require a medium to travel. It can travel through vacuum. Light, yeah, electromagnetic wave. So that's the problem with the speed of light. So you know what light is? It's an electromagnetic wave, and the wave equations that you saw me
halfway drive, the first day of class, it was based on Maxwell's equations in vacuum. So there's no medium to speak of whatsoever. And do you remember what the expression for speed of light was? Or C?
Over square root mu naught epsilon naught.
Yeah. 1 over square root of mu naught epsilon naught, or approximately 3 times 10 to the 8 meters per second. And this expression is problematic. To a physicist who believes in principle of relativity, this expression is a bit problematic. Let me try to sketch the picture why. Imagine you have a train like this. And we will imagine that the train is moving at some speed. And we'll say it's moving fast enough. I'm just going to call its speed v. Because, I don't know, it's a choice between writing down something that's kind of unintuitively large versus leaving it as a symbol. Let me leave it as a symbol. Train moving at speed v. And let's say you have a source of light. You have a laser pointer or a lamp, something here that's emitting light waves. And if this v is 0, then you know how fast the light wave's moving. It's moving at speed c, that way. Or here, it's moving at speed c also, right? So once the train starts moving at speed v, what does your intuition say about the speed of light here? So as you're looking at the light from out here, how fast should the light be moving? Yeah, your intuition says that, well, the source is moving at speed v, so it's the speed of the source plus the speed of the wave. That's how fast it should move. And here, this is how fast it should move. That's what your intuition tells you. And this leads into a bit of a problem. So what you are claiming here is that this is speed of light, right? C plus v speed of light, which means, according to the formula we derived using Maxwell's equation, it must be equal to 1 over square root of mu naught epsilon naught. What are mu naughts and epsilon naughts? They're constants. They are, permeability of free space and permittivity of free space. These are constants that apply to vacuum. And here we had an out. We could say this reference frame is special. This is the reference frame where air is at rest. But you cannot say that this is a reference frame where vacuum is at rest. Vacuum is nothingness. It makes no sense for vacuum to be moving or so. So that's the problem that you come across. So I guess here's another way to phrase it. So we say laws of physics are the same in all inertial reference frame. Laws of physics, according to Maxwell's equation, determines the speed of light. So if the laws of physics are the same in all reference frames, it must mean that speed of light given by this is the same in all reference frames. That's what it has to mean if principal relativity is correct, and I guess Maxwell's equations are correct. And for us today, it's actually not that difficult for us to say Maxwell's equations are correct. The theory of electrodynamics that we have known for a century and a half is not incorrect. But for the scientists living in the late 19th century, this was a harder jump because it's a recent discovery for them. Even when Einstein published his paper on special relativity, was it 1905? I forget the exact year. So he wasn't born that long after Maxwell came up with his Maxwell's equations and predicted electromagnetic wave. So because we're going to go into a bit of a history about special relativity, I just want you to acknowledge that it was difficult for people at the time to accept this fact that we are going to start out with as one of the postulates of special relativity, that because of principle of relativity, laws of physics are the same in all inertial reference frames, and the laws of electrodynamics are also laws of physics. and laws of electrodynamics are the same in all inertial reference frames, that means one of its consequences, the speed of light, is constant in all inertial reference frames. In physics, we don't repeat ourselves a lot. You won't really find any physical laws that are that duplicate each other. Like if you have something that's stated as law of physics, in some way we are like mathematicians. If you build an axiomatic system of mathematical system, usually you have an axiom because it's absolutely necessary. You don't have two different axioms that do the same thing. So when we, in about 30 minutes or so, when we get to postulates of special relativity, the second, what we call second postulate of special relativity is the one physical law that maybe you'll be told that essentially repeats something that you already know. And what it reflects is the hesitation on the part of the 19th century physicists to completely accept the new theory of electrodynamics. And that's the bold assumption that Einstein makes when he comes up with a special theory of relativity, or theory of special relativity. So, so this picture that we were trying to draw based on our intuition, it's wrong. All of this is just wrong. And we can see that because it's contradictory with other things. And we are going to have to draw up a new picture that's going to be consistent with all the laws of physics, as in how they fit into each other. So let's take the break now. And when we come back, I want to describe an experiment that helped people accept this reality that speed of light is constant in all inertial reference frames. But as we go into that, this is really the maxim I want to leave you with. No one is born with the intuition in special relativity. So as we go through in special relativity, the thing that will make your life easy is if you accept that all of you have wrong intuition. I had wrong intuition until, I don't know, 2007, until about 10 years ago. So no one comes into special relativity having any kind of correct intuition. So if your intuition and your math disagrees, the math is probably right. And the hard work in special relativity is reforming your intuition so that it actually agrees with the reality. And so let me just leave you with that, and we'll go through some of the things that more thought experiments and actual experiments that will help us realize how we have to change our intuition. Yeah. Welcome back. So this is a historical experiment that I want to just describe quickly because it's actually useful setup to consider what's going on with this new reality of nature. So, but to be clear, to be historically correct, Einstein was not influenced by this experiment at all. So when you look up Einstein's work, his original work on special relativity is what he titled Electrodynamics of Moving Bodies. So he was a theorist. So he was interested in it purely from a theoretical point of view. But what this experiment is good for is for other doubters, other people who doubted that Einstein was correct in assuming that Maxwell was correct, another theorist, that this experiment proves for those other people that Maxwell was correct and Einstein is also correct. So we covered this when we did optics. So I will just go through this quickly without undue wasting of time. So you know, you have, so Michelson-Morley didn't have laser, but they have some source of light coming in, split it into two parts, combine it back. You can see the interference fringes like this picture here, right? We covered that. And so what Michelson and Morley thought they could do with this interferometer is they thought they could measure this change in speed of light. And there's an underlying theory behind it. So what some people were doing was they were introducing this mysterious substance called luminiferous ether. whose sole purpose is to serve as a medium for light. This luminiferous meaning light carrying in Latin. So what Michelson and Morley were trying to measure is they were trying to measure the ether drift, or how fast is Earth moving through ether. So, so let's say, just as a matter of labeling things, let's say ether is drifting this direction. So this is the direction of, I don't know, ether wind. That how fast this mysterious medium for light is moving. And for all these people who didn't believe in Maxwell, you'd say the Maxwell's laws hold correct in the reference frame where ether is at rest. So speed of light is c, if in the reference frame this ether is stationary. So if ether is moving in one direction with some speed v, then they would say, oh, then in this reference frame, speed of light is faster going that way, and it's slower coming back. You can almost think of this like a current. So you have a boat that has a, I don't know, water speed of 50 meters, that's too high, 20 meters per second, and if it's moving against the current, that from the shore it'll look slower, and if it's moving with the current, it'll be faster from the shore. That basic idea. So in the simplified of the Michelson-Morley experiment, you would imagine it this way. In your lab frame, you have one light beam that's being sent this way. You have light beam that's sent up, bounces against the mirror, and then comes back. And you have another light that's sent this way, bounces against the mirror, and then comes back. Okay? And now what you have to, so I guess for this direction, it's kind of easy to imagine what would be going on if this whole ether idea was correct. You would say going that way, speed of light increases. So going this way, light moves at a speed of c plus v. And then coming back, the light wave is moving against the current. So it's c minus v coming back. Yeah? And this direction is actually a little bit more tricky. So imagine this way. If the light was actually aimed directly at this mirror, would it actually reach the mirror given this presence of ether wind? So how should it be directed? Should actually be directed at an angle this way, right? So let's say, that's how we directed the light. So the actual direction of light, it kind of goes this way. So, and then it strikes it, and then it comes. So for a one-way trip, this is the actual distance being traveled. Instead of, so if this apparatus has the arm length of d, let's say they both have the same arm length d on both sides, then on this arm, you would say that the distance traveled is 2d, one way that way and then back. On this side, distance traveled, you have to be a little bit more careful. You're not traveling 2d because it's actually working against the current, so it has to use a component of velocity against the current. Yeah? So we can actually derive a quick formula and do a quick estimate to see that Michelson and Morley should have been able to see this ether wind. So this is an example of a null experiment where experimentalists actually saw nothing. So you would think, doesn't that mean they failed? Like, this happens a lot in actually other fields, like in psychology. People hypothesize some effect, you do an experiment, you see nothing, and that doesn't get published because no one's surprised by the fact that nothing happened. But sometimes there's such a heavy expectation for finding something. The fact that you found nothing actually becomes a surprising fact that you have to try to explain in your theory. So let's see. I think the way I can do the calculation is, let's do it in terms of the time difference. And and when I plug in the numbers, I will compare the time difference with some, let's say, frequency of light, because that's going to give you when you are going to get one fringe of difference, right? So I will plug in the numbers in later, but I want to just drive a few formulas first that I need to plug in numbers to. So the two formulas I want to derive is the round trip time for this arm and the round trip time for this arm and the difference between them. Okay? So if velocity is 0, those two round trip times should be the same. But when they're not, they're different. So okay. So let me call this arm 2, this arm 1. So I think a round trip time for this is easier, so let me do that first. So round trip time T2 is time that takes to get there. So that's d divided by, so speed is length by time. So time is length by speed, right? So distance divided by c plus v, and the trip coming back plus distance divided by c minus v. Okay, so that direction of ether wind means this apparatus is moving this way. So going that way, it should take shorter, because this is moving towards the light source. And going back should take longer because the target is moving away. Okay, good. So you have this fairly simple expression. And since it's so simple, let me simplify it a little bit. I can actually combine these two fractions. So factor out d and combine the two fractions. So it's a d times product of the bottom. Does everyone recognize these two products as being c squared minus v squared? Yes, good. Okay, on the top, it's a c minus v plus c plus v. C minus v plus c plus v. So v's cancel, nice. So I have 2c divided by all of this. So let me actually write that out. That's going to be, and then factor out c. Let me write it out this way. It's going to be 2 times d over c times 1 over 1 minus v squared over c squared. Is this correct coming from here? I've done a couple extra algebra for some reason. Good. Multiply top and bottom by c, then you should get c divided by c squared minus v squared, which is what this is with this two. Good. All right, so that's my T2. Let's compare this against T1, time it takes to get there and back. So there I have to know, let's see. So I have to know this distance, which is not given to me. But, well, so this distance I could express it as v times T1 divided by 2. That's how long it takes to get there. This is the distance traveled in that much time. All right. Okay, then I think I know this distance, right? It's a Pythagorean theorem, right triangle. This distance is still d. So this distance that the light is traveling in time of, so this travel happens, so when this happens here time is T1 divided by 2, half the amount of time of the whole full round trip. And coming back, it would take the same amount of time, right? Okay, so let's calculate for this time. So I can say this T1 over 2, amount of time it takes, is the distance, which would be square root of d squared plus v times T1 squared, v squared T1 squared over 4, square root it, divided by the speed. It's moving at speed c. So c. All right. So this is where, hopefully, if you are observing carefully, you would realize that I'm not done. I have to do a little bit of algebra because I have T1 here and here. I want it solved entirely in terms of T1, in terms of everything else. So I have to do that bit of algebra. So let's just go through and do it. It's not that long of an algebra. So square both sides, then you get T1 squared over 4 is equal to 1 over c squared times this, no longer square rooted, d squared plus v T1 squared over 4 still. Good. Let me collect like terms of T1. Then you end up with 1 over 4, or let me factor out T1 squared over 4. So T1 squared over 4 times 1 minus 1 over c squared times v squared. So minus v squared over c squared. Good. That's this thing moved over, and the rest are d squared over c squared. Yeah. So move this over to here, take the square root, move the 4 over also. Then you get this result for T2, which is remarkably close to this. T1, sorry. You get this for T1. T1 is equal to 2 times d over c, 2d over c times. And the only difference from this is instead of just being this, 1 over 1 minus v squared over c squared, you have to take the square root of it. So there's a power of 1/2 here. That's the only difference between, label 2 here, between this is T2, between T2 and T1. So let's just plug in some numbers. I want to just plug in some reasonable numbers and see if this kind of experiment can be done to see an interference pattern. So we are talking about remarkably short amount of time, like nanoseconds. So, but I think you will actually see something. So let's try that. Let me use Wolfram alpha because that'll make me not deal with units. So which one is longer? Is T2 longer or T1 longer? I think T2 is longer. Yeah. So let me do T2 minus T1. So algebraically, that will be 2 times D divided by C times, so 1 over 1 minus v squared over c squared minus square root of 1 over 1 minus v squared over c squared. Good? Okay. I'm going to use a bit of Wolfram language to plug in numbers. There's a syntax called substitution. I'm going to put, what should I put in? What's a reasonable length for Michelson interferometer? 2 meters? So let's say a meter. I'm just doing order of magnitude calculation. 1 meter. C, hopefully it gets it that C is the speed of light. What is a reasonable speed for experiment like this? What do you think Michelson and Morley used for speed of ether wind? So now they were rotating something. They were actually rotating the apparatus. So they would set this up, and then they would rotate it by 90 degrees. Like, what would they be doing? It's not rotate. It does have something to do with Earth, but it's not the spin of the Earth. It's something else. Orbital speed. Yeah, rotation around the sun. That's actually pretty high. Let's just look that up. Orbital speed of Earth. So, that's just some reference number to start out with. 108, let's see, is that in meters per second somewhere? No? Okay. Wait. Okay, 30 kilometers per second or 30,000 meters per second. Let me put that in. So V would be 30,000 meters per second. So it's actually pretty high. I think that's everything, right? Let's see what we get. So when you put those numbers in,
They rotate this apparatus at 30,000 meters per second.
no, so the idea is that, so with the interference, the pattern you get, it doesn't really tell you anything. It's the change in pattern you are looking for. So you set up this apparatus, having it arranged this way, seeing some kind of interference. And as you rotate it, you are looking for that shift in the interference fringes. Good? Yeah. Yeah. So, but the V that you are using for reference is the speed of Earth around the sun, assuming the ether is stationary around the sun and all that stuff. All right. So let's see. Did they? Okay. They are not putting in a number for C. Let me do a number for C. C is about 3 times 10 to the 8 meters per second. Once again, I'm still using Wolfram language. Okay, 3 times 10 to the 8. All right, so it gets, did I do something wrong? Oh, correct the formulas. 1 meter, 30,000 meters per second. All right, for the time, we get 10 to the minus 17 seconds. That doesn't sound like a lot of time. In fact, that sounds awfully short. Let me try converting it to wavelength, because wavelength is what I have intuition for. So it was 3 times 10 to the minus 17 seconds, right? So wavelength would be, so wavelength is speed of light divided by frequency, or speed of light times the period. So speed of light is 3 times 10 to the 8 meters per second. And for the time, I'm putting it 3 times 10 to the minus 17 seconds. Let's see what that gives us. So about, I should have done this number ahead of time, 9 nanometers. Is that comparable to the wavelength of light? It's getting close, right? So we started out with saying d is equal to 1 meter. Well, I can go from 1 to 10 meters pretty easily. I can fold this up. And in fact, that's what Michelson and Morley did. So when unfolded, the d would work out to be something like 10 meters instead of 1 meter. So now this would be, 90 nanometer. So that's about a fifth of the visible wavelength of light. So they weren't quite expecting to see one full cycle. But if this is what I want you to imagine. If you had this interference pattern, and if this pattern shifted by a fifth of a whole cycle, would you be able to see that with a careful observation? Yeah, you would be able to see this edge moving out to a little bit, right? So there's a lot of careful experimental work to be done. But even just checking it visually, no electronic measuring devices, Michelson and Morley had enough sensitivity to be able to see this ether wind coming from orbit of Earth around the sun. And when they did it, they got nothing. And in fact, they were able to put a limit on how fast this V can be. I don't remember the number right now. It was substantially smaller than Earth's orbit around the sun. So a lot of people came up with the theories to explain this null result where you saw nothing. And one of those people is actually Lorentz. So let me end up this or wrap up this particular segment here. So a guy called, let me erase all this algebra that we've done it, so we don't need to see it again. A guy called Lorentz came up with this idea that we now call Lorentz contraction and dilation. So the idea he had was maybe as these objects move around in ether, they change their lengths. So as this moves this way, the ether wind changes the length of this arm so that this arm gets shorter. And when he was working it out, he also figured then also the the time has to somehow change. I don't forget the details. His the conceptual understanding was flawed, but he came up with a mathematical transformation that could explain this null result, how this experimental setup would physically change so that when you do the calculation of these 2 times, according with those changes, you gave 0 time difference. And we will come back to this later today while I'm getting observed. But this is the historical background I want you to be aware of as we go into how Einstein approached this.
So let me get started. Before we got to this point, we talked about the first postulate of special relativity, which one might call the principle of relativity. That is, laws of physics are the same in all inertial reference frames. And you might call this principle of relativity. And it's a really old principle. Galileo is often credited with having realized it with his like a sailor in the underhold of a ship. Could the sailor figure out if the ship is moving or not, if it's a really gentle ride? We talked about that already, so let me just leave that be. Now, this is what we will call first postulate of special relativity. It's special relativity is special of all the theories, laws of physics that you might learn. So especially in contrast to the quantum mechanics that we'll cover soon. Special relativity can be almost mathematically derived. A lot of things in physics, it took a lot of experiments for people to figure out what the laws are. Maxwell's equations in electromagnetism, they were like that. Each equation had to be discovered by someone doing experiments. It's only at the near the very end where Maxwell could discover his Maxwell term in the Ampere's law by theoretical investigation. And the really special and remarkable thing about special relativity is that you can mathematically derive everything in special relativity from these 2 principles and all the other existing laws of physics. So I gave you the first postulate of special relativity, and the second postulate of special relativity is this. It's let me state it in the way I think it's typically stated. The speed of light in vacuum is always at a constant value that we have given the letter c to. C is approximately 3 times 10 to the 8 meters per second. And I think maybe if we want to emphasize, you might emphasize it this way. It's always at c in all inertial reference frames. One might think that's kind of an odd and specific thing to say, unless you heard about it before from popular science and whatnot. So the way I like to call this, the way to give it a succinct name that I hope people will remember is this name. I like to call this correctness of Maxwell's theory of electrodynamics. Well, I guess that's kind of long. The reason I call it this way is because if you assume that what you learned about electromagnetism in physics 4b is correct, which, why wouldn't you assume that? Then it follows from the first postulate that laws of physics, which contains Maxwell's theory of electrodynamics, laws of physics says light travels at c. This is actually something you can derive. From Maxwell's equations, you can derive a wave equation. And that wave equation says the electromagnetic wave has a speed c, or in terms of the constants in the electric and magnetic things in the basic SI unit, it goes as 1 over square root of epsilon naught mu naught. I think that's right. So since this expression falls out of a law of physics, Maxwell's theory of electrodynamics, if Maxwell's theory of electrodynamics is correct, then this must be correct, that speed of light in vacuum is always sc. And I think from our perspective, in the 21st century, it might be kind of odd to say this as an explicit thing. But in Einstein's time, at the turn of the century, beginning of 20th century, Maxwell's theory of electrodynamics was pretty young, I think less than 50 years old. So there were some people who tried to come up with corrections to Maxwell's theory. That's what the whole search for luminiferous ether was about. And Einstein's bold assumption is to assume that this new, less than half century old theory is actually correct, that it can be pushed to limit and it won't break. So those are the two postulates of special relativity. And unlike almost anything else you do in physics, you can build the rest of the theory of special relativity out of these two postulates, like you are, deriving theorems and lemmas and stuff that mathematicians do when they develop like axiomatic set theory. So these postulates, you can almost think of it like axioms of special relativity, except, axioms are more of a mathematical thing, and we physicists prefer the words like a postulate and hypothesis and principle. So in principle, you can derive everything in special relativity from these two postulates. So let me do it first application, which is this what we are going to discover as relativity of simultaneity. So you're going to hear about a lot of thought experiments or Gedanken experiments, which is describing a setup and assuming that all the laws of physics that we know are correct, including these two postulates of special relativity, and then following its consequences. That's all we mean by thought experiment. It's no more exotic than that. So let me draw this picture for you. So imagine we have a vehicle, a relativistic train that's going to have some stuff set up. Let's just describe it concretely. So it's got some length L, it's how long it is, and it's equipped with a special device. In the middle, or very middle of the train, the device is called a light bulb. Oh, I guess it's not that special. It's just a light bulb. It's a pulsed light bulb. I guess that's what's special about it. You can emit a single pulse, and you can kind of, it emits a pulse of light, and then it travels the way light travels. And it's got two more special devices. There's a detector at the front of the train. I'm going to say train's going to end up moving that way, so this will be the front. Let's call that front F. And at the back of the train, let's call that B. Oh, that's going to be so confusing. Rear, let's call that R. Rear of the train. There are detectors. So when you emit this pulse of light, the detectors at the front and the back can detect when the light has arrived. So when they are functioning, they can measure time at front when the light pulse has hit the front, and the time at the rear when the light pulse has hit the rear of the train. Good? I think all of that hopefully makes sense. So I think if you imagine me lighting this up, emit a pulse, then the way I've set up where this is in the middle, hopefully you have this intuitive sense that by the time light pulses hit those two detectors, these two times, the TF and TR, should be the same. Good? And this is what someone might call simultaneous at the same time, meaning these two values of time are the same. So that's what we are used to experiencing. You can set up experiments in such a way that when you do that experiment, you get simultaneous things. And just to keep with the tradition, we can say that Alice is riding in this train. So Alice is the one who oversees all these experiments and makes sure, the TF is equal to TR. I I inspected all the equipment. There's nothing broken, nothing misbehaving, and Alice signs off her name to the fact that yes, these two are simultaneous. Now we want to imagine that this train is moving at some decent speed, let's say 0.833 c, about 83% of speed of light. Very realistic. And we are going to introduce a new person, Bob, who's not on the train, but he's the station manager. So Bob is standing here outside the train, looking at this train, moving at the speed, 83% of speed of light. And when Alice comes back to Bob saying, yeah, I set all this up, I measured the times, they were simultaneous. Bob tells Alice, that's not what I saw. I saw light hitting one end faster than the other end. I think if I'm getting it right, when Bob measures those times, Bob will measure it such that the time that the light hits the rear is earlier than the time that the light hits the front. That's what Bob says. And he says Alice is wrong. So, who's right? Is Bob wrong? Because, he's kind of far away from the equipment. So maybe that's why he didn't see it correctly. By the way, I want to make sure that we draw this distinction between seeing and observing. And watch how I didn't put Alice in the middle of the train, because it really wasn't necessary. So if I'm describing what Alice sees, Alice will actually see what's happening up here. She will see this earlier than what she sees back here. But, Alice is smart. She's not stupid. She's smart. She knows that she's closer to the front than the rear. So she knows that when she sees this event happening before, she knows that, that's happening because I'm closer to it. She knows that when she sees this event happening later, she knows that, it's because there's a travel time for the signal. That's why I'm seeing that later. So because Alice is smart and aware of light's finite propagation time, she makes those corrections. She corrects it for, the distances, and the conclusion that she draws after having made all those corrections. That's what we are going to refer to as observing. So whenever we are using the word observing, what we are saying is that all those tiny little minor, really trivial corrections have been made. And what remains is a true, real relativistic effect. So where Alice is, where Bob is, it actually doesn't really matter. The only thing that matters is what reference frame they are in. So let's try to describe what's happening here from Bob's reference frame. So the way this is drawn, the train appears stationary. So let's actually, make a copy of it down here and redraw it so that we can draw it from Bob's perspective with the train moving. So let's break it up into a few snapshots. So there's that moment in time, and I guess we don't really need Alice, so let me not draw her. Trying to draw fewer things. So there's this snapshot that's drawn is the moment in which the light was emitted. Okay, the train moving forward at 83% of speed of light, it'll be moving forward, and let me draw in green where the train will be at some point later. Let's say in the amount of time that light travels to, not quite here, but in the amount of time light travels to somewhere here, about halfway, and somewhere there, about halfway, train has moved. And the train will have moved, I think, I'm trying to draw it to scale. Maybe something around here, it'll have moved to position like this, from snapshot 1 to 2. This will be the position of the train in snapshot 2. You can see that between these two and the next equal sized time interval, the light will hit the train, the rear of the train. Let's mark the location here. There will be an event, detection of this light pulse at the rear of the train. And let me label the time there with not TR because I think that gets confusing, let me prime it so that it's a different symbol for a different number, potentially. Now, while that's happening, I think in the snapshot 3, in about equal amount of time, the light has traveled to here. Front of the train keeps moving. Let me draw that in purple. So in that equal size time interval, the front of the train will have when something like this. So, in snapshot 3, the light hasn't quite hit it yet. So it'll take, snapshot 4, 5. At some much later time is where the front of the train finally gets hit by the light pulse. And now you register the time, t front. I'm not drawing this to scale. But from the description, you can kind of see why Bob would say what he said. That when he observed these two events of the light hitting the back of the train and the front of the train, that the event of the light hitting the back of the train occurred at an earlier time than the light hitting the front of the train. It's a quite strange and counterintuitive effect. I think we are used to thinking of an absolute time. We are used to thinking that if we have something that is simultaneous, we are used to thinking, assuming, presuming that simultaneity is universal. That if something was simultaneous for Alice, that it must be simultaneous for Bob. What we are seeing in this application of the principles of postulates of special relativity is, and I don't think I have even explicitly invoked any actual postulate of special relativity, other than that, light is traveling at speed c. And I guess, so I didn't explicitly invoke it, but if you are dealing with sound waves, for example, the way you would resolve this apparent contradiction is to say, oh, that's because so in Alice's frame, these two waves are traveling at the same speed. But in Bob's frame, you would say, oh, they are not traveling at the same speed. The one that's moving towards the front of the train, it moves at the speed of its own speed plus whatever speed the train is moving. And the one that's moving backward, it's moving at whatever its own speed is minus the speed of the train. Like for sound waves, that's how you would resolve it, and you would say that the event of arriving at the back and arriving at the front, they happen at the same time. So in the classical mechanics description, simultaneity is universal still. And what we are saying is that even though this is how we would handle things in a natural, intuitive way, what we are going to say from here on as we venture into special relativity is we are going to say explicitly that we don't trust our intuition. What we trust in is the postulates of special relativity. These are the absolutely true statements that are never wrong, even when they sound wrong. So even though the statement that the speed of light is always sc in all inertial reference frames, it'll sound wrong to you until you get used to it, because you will want to correct the speed of the light. And what I ask you to do as a competent, good mathematician is to say, ignore this impulse, hold on to your axioms, say that what is true is the second postulate of special relativity. Light always travels at speed c, even when you don't want to say that's true. So under that assumption, what I said is, light hits the back of the rear of the train before it'll hit the front of the train, because the light going towards the front of the train isn't moving any faster from Bob's reference frame. It's still moving at c. Light going to the rear of the train is not any slower. It's also moving at c. Now, they are different in other ways, and the way they will be different, they'll be different in frequency. That's what will lead to something called the Doppler effect that we'll, I think, look at in later, maybe next week or the week after. So they are different in some other aspects. Their frequency can change, their wavelength can change, but what doesn't change is their speed of light. So yeah, what Bob observes of these two events is that they are not simultaneous. And this is what leads us to say simultaneity. So, whenever two events appear to happen at the same time, that's what we call simultaneity. Simultaneity is relative, meaning if you have two events that is simultaneous in one inertial reference frame, like a TF and TR was here, then it's, especially if they are separated in space, then it is possible to find another reference frame where they are not simultaneous. And I believe, especially in lower division textbooks, this fact is not given enough emphasis. And that leads to a lot of confusions in like a special relativity paradoxes that some of which we'll see next week. So I wanted to cite this textbook that I like really a lot. I brought a screenshot here so that I can refer to it in this lecture. This is a screenshot from digital version of a textbook called Revolutions in 20th Century Physics by a really popular upper division textbook author, David Griffiths. And this particular textbook is actually not written for upper division content. It's written for physics for humanities majors. But I think it's worth reading even for engineering or future physics majors, because there are certain insights that's so succinctly summarized that as a lot of students are going through this physics first class will miss unless they take care to pay attention to it. It's this paragraph that I want to refer to. Relativity has nothing to do with what you observe, or relativity has to do with what you observe in the sense that we are talking about, not what you see with all the spurious effects. We are talking about real effects, not appearances. And it's this sentence I want to bring your attention to. Einstein liked to say that all the conceptual difficulties of special relativity derive ultimately from the relativity of simultaneity. And as we explore relativistic paradoxes, you will see how many, I hope you will be surprised by how many of the paradoxes do ultimately get resolved by correct understanding of simultaneity. So maybe this will be illustrative. So let me try to set this side by side, and I want you to just think through and understanding that you haven't had much time to think about special relativity beyond just learning that just now maybe that second postulate of special relativity says that light always travels at speed c. See if what this Errata submission is trying to say is something that you would have agreed with. So this submission is referring to this picture here, and I guess it might be worth the time to for me to just to read through. Well, actually, read through the whole section. So let me do that. Well, whole section. Yeah, let me read through the whole section. I think I can do that in about 10 minutes and it'll be worth the time. So this is section 5.2. It says, so starting from here, do time intervals depend on who observes them? Intuitively, it seems that the time for a process, such as the elapsed time for a foot race, should be the same for all observers. In everyday experiences, disagreements over elapsed time have to do with the accuracy of measuring time. No one would be likely to argue that the actual time interval was different for the moving runner and for the stationary clock displayed. Carefully considering just how time is measured, however, shows that elapsed time does depend on the relative motion of an observer with respect to the process being measured. And I want to make this a little bit more broader. It's not about elapsed time alone. It's about simultaneity, as the section says, relativity of simultaneity. And we'll get to that. Consider how we measure elapsed time. If we use a stopwatch, for example, how do we know when to start and to stop the watch? One method is to use the arrival of light from the event. For example, if you're in a moving car and observe the light arriving from a traffic signal changing from green to red, you know it's time to step on the brake pedal. The timing is more accurate if some sort of electronic detection is used, avoiding human reaction times and other complications. Um, okay, let me just move on. I'll bring that point on later. There's something I want to mention, but next week might be a better time to bring it up. In the lecture, you will see that there's a distinction between what I call seeing and what I call observing in this class. Now, suppose two observers use this method to measure the time interval between two flashes of light from flash lamps that are a distance apart. Observer A is seated midway on a rail car with two flash lamps at opposite sides equidistant from her. A pulse of light is emitted from each flash lamp and moves toward observer A, shown in frame A of the figure. The rail car is moving rapidly in the direction indicated by the velocity vector in the diagram. An observer B, standing on the platform, is facing the rail car as it passes and observes both flashes of light reach him simultaneously, as shown in frame C. So here he sees both flashes simultaneously. He measures the distances from where he saw the pulses originate, finds them equal distance, and concludes that the pulses were emitted simultaneously. However, because of observer A's motion, the pulse from the right of the rail car, from the direction the car is moving, reaches her, observer A, before the pulse from left, as shown in frame B. So the light was emitted here, it traveled some distance. Light was emitted here, it travels some distance. In that time that the light travels that some distance, observer A moved towards the right side light. And the light from right side reaches her before the right light from the left side. She also measures the distances from within her frame of reference. She's at the midpoint between the two, finds them equal, and concludes that the pulses were not emitted simultaneously. So far, so good. The two observers reach conflicting conclusions about whether the two events at well-separated locations were simultaneous. Both frames of reference are valid, and both conclusions are valid. Conclusion one being observer B says they were simultaneous, and conclusion two being observer A says they were not simultaneous. Whether two events at separate locations are simultaneous depends on the motion of the observer relative to the locations of the events. Here, the relative velocity between the observers affects whether two events distance apart are observed to be simultaneous. Simultaneity is not absolute. We might have guessed incorrectly that if light is emitted simultaneously, then two observers halfway between the sources would see the flash simultaneously. But careful analysis shows that this cannot be the case if the speed of light is the same in all inertial frames. And we might analyze this in more depth in a bit after we go over this. This type of a thought experiment, in German, Gedanken experiment, shows that seemingly obvious conclusions must be changed to agree with the postulates of relativity. The validity of thought experiments can only be determined by actual observation, and careful experiments have repeatedly confirmed Einstein's theory of relativity. And this is what I mean that the second postulate is true. It's been repeatedly tested, and the conclusions that follow from second postulate has been confirmed over and over again, which is the basis on which we say second postulate is true. Now, when you heard me read through this section, that most of it made sense.
Now, let me read this errata, which I'm telling you ahead of time is wrong. So, so with that caution, see if you can spot the point at which this is wrong. So this is what someone who is usually people submitting errata are physics instructors. So I don't know who wrote this, but I'm assuming he or she was a physics instructor. So this is what someone also who is experienced in physics are saying. The section that describes how observer A perceives the two flashes of light. Observer A will see both flashes of light from the right and the left arrive simultaneously rather than the right before the left as described in the text. This is because observer A is in an inertial frame of reference, and thus she is entitled to say that she is at rest and the platform is moving. So in her inertial frame, she and the two sources of light are at rest, and thus light from both sources would reach her at the same time. If the light from both sources did not reach her at the same time, she would be able to tell that she is the one who is moving, and this will contradict the first postulate of special relativity that the laws of physics are the same for all inertial frames. Observer B, however, would see that the light from the right reach observer A first because she is moving towards the light, and thus, as perceived by observer B, the two flashes of light will not reach observer A simultaneously. I think you can actually see something that's within the within this description here that's internally inconsistent, because whether these two lights arrive at the observer A at the same time or not, that's an unchangeable fact. So if these two flashes of light arrive at observer A at the same time in her reference frame, then that particular fact would be the same regardless of what other reference frame you are in. So this second part is just contradictory to the first part. If observer A sees these two lights at the at the same time, then observer B should also observe that these two flashes of light arrive at observer A at the same time. So ignoring that second half, which is kind of easy to disprove based on logic alone, if you were reading here and didn't have me to tell you that this is erroneous, where is this errata submitter wrong? What mistake did they make? I want you to think it through for a bit, and I'll tell you. And this happens quite commonly when people make mistakes regarding relativity of simultaneity. In fact, the textbook encourages probably too strong a word. Textbook description doesn't prevent this kind of mistakes here. So this is the textbook description of these events. So textbook says, now suppose two observers use this method to measure the time interval. An observer A is seated midway. Here it is. A pulse of light is emitted from each flash lamp and moves toward observer A, shown in frame A of the figure. That's all it says. And I think this is the place where if you are writing written words on a textbook, it takes a finesse to one, not mislead and be accurate. So in the textbook, they were careful not to specify in what reference frame these flashes were simultaneous. I think the way A is drawn encourages people to think that they were set up to be simultaneous in observer A's frame. And I think that's why mistake like this can be easily made, even by people who are educated in physics. Because once you start from the mindset these were simultaneous in observer A's frame, then this is the only consistent thing. And so in the textbook, they try to describe how these pulses were not set up to be simultaneous in observer A's frame. They were instead set up to be simultaneous in observer B's frame. So if you want to be more clear, then you can even describe a kind of a triggering mechanism. Maybe there's a kind of a triggering device here. You measure them ahead of time so that you make sure these endpoints will pass those two triggering points at the same time. And as they do, you trigger them. And the important thing here in special relativity, whenever you say at the same time, you have to specify the reference frame. So in this textbook description, they didn't quite describe in detail how these will be triggered simultaneously in observer B's frame. But you can think of a contraption that would do that. And so having been set up to flash simultaneously in this frame, that's what they did. And whether these lamps were moving with the train or not, that's not quite relevant. Although I guess because they are moving with the train, if you wanted to set up a contraption for triggering these simultaneously in the train's reference frame, that is actually easier than triggering them simultaneously in the observer B's reference frame. In fact, that's what I'm describing in the lecture here. This setup is something that can be used to trigger these two lamps simultaneously in the train's reference frame. And what you see here described is that once you've set up that way, set it up so that this light pulse will reach A and B simultaneously, then what you will find is that working through this here and applying the second postulate of, I guess I kind of describe it around here also. So in the reference frame of the guy who is on the train station, the light pulse that reaches the back end of the train, that reaches it before the light pulse that reaches the front end of the train. So once you set up on a set of events to be simultaneous, or a pair of events to be simultaneous, you have to pick a reference frame in which they can be simultaneous in. And I think with the tools we are introducing this week, if this is leaving you maybe confused, I think I would rather you be confused than to not fully absorb the fact that simultaneity is not an absolute thing in special relativity. That whether two events are simultaneous or not, it depends on what reference frame you observe them in. And so the way it's set up in this lecture here, I set up the events A and B to be simultaneous in the reference frame of the train. Therefore, when you observe it in a frame that's moving relative to the frame, then they are no longer simultaneous. In this textbook section, without describing in detail how they would do that, they set it up so that these two flashes would occur simultaneously in this reference frame. Having set it up that way, they are not simultaneous in observer A's reference frame. I think all of this is, I think that as clearly as I can describe it at the moment. Maybe let me end this with more of a foreshadowing for next week, when we'll have a much less confusing analytical tool that will help us both diagram this and describe it very accurately with not as much room for misunderstanding or ambiguity or anything like that. Um, to me, the moment when special relativity made sense was when I learned to use something called a space-time diagram. And it's a tool that is introduced in your textbook. I forget which section exactly. It might be section 5.5. And I will you will see me use this tool of space-time diagram much more extensively than your textbook does. This is an example of space-time diagram, but I don't think that's quite. So I think if this discussion of relativity of simultaneity is leaving you feeling confused, I think that's fine. As far as what we are doing this week, I would much rather that you take this time to unlearn something that you've learned unconscious or subconsciously until now, which is that the idea of something happening at the same time is not something that requires a specification of reference frames and coordinates. That's what we've been doing up until now, and I want you to unlearn that whenever someone says things like at the same time or simultaneous, that's a phrase that requires a definition of coordinate system. As much as if I describe something as being along the x-axis, then you would want to know how I'm defining my x-axis. And those axes that need to be defined, and they obey certain kind of geometric properties that is described here. It's these axes that you see described there, and this is subsection within section 5.5, where you will see that description of simultaneity. So what this is showing here is that this left and the right flash, they were set up to be simultaneous in this coordinate system that's described as our resting frame. That would be the frame of this guy, observer B. And the reference frame of observer A, it's described with an axis that looks like this, x prime and ct prime. These axes have rotated. And these lines that are parallel to the x prime axis, that's where time has the same value. So these are the set of points that are simultaneous with this event in the reference frame of the train. And these are the set of points that are simultaneous with the right flash in the reference frame of the train. And looking at this, what you see is that the right flash does occur before the left flash does. This is more negative time than the left flash. Where I want to leave you at is unlearning some of the classical intuitions that you've been relying on so far, because place where it really trips up even the people who are experienced in physics is the relativity of simultaneity. I think it usually trips you up when you have assumed the simultaneity implicitly. And you will see that in some examples of paradoxes we'll go over either next week or the week after. So.
Hi, this is the lecture on space-time diagrams. So far, in our discussion of special relativity, you have seen space-time diagrams. I've drawn them a couple times. The purpose of this lecture is to collect in one place all the salient points about space-time diagrams and also demonstrate its use with one or two examples. So this is the aspect of space-time diagram that you have seen. You have an axis representing time and position dimensions.
I usually label time dimension as CT to indicate that both axes are in the same unit and that both the dimensions are comparable to each other. As you look at these space-time diagrams, if these remind you of motion graphs that you have seen before, then I want to encourage that, because really this diagram is not really new. What's new here is how we use these diagrams to clarify concepts and precisely and clearly specify the special relativistic situation that we discuss. Let me give you a quick reminder of what motion graphs look like. Here in this simulation, I have two objects. One object has some initial velocity, and I set up a plotting thing to plot the position of this box as it moves across. This is motion graph, and you have seen this earlier in your earlier physics classes. The only difference between these motion graphs that you have seen and the space-time diagram that you will see are how the axes are labeled. In the motion graph, we are interested in quantities like position, velocity, and acceleration, and we plot them on the y-axis. And time is represented as an independent variable. What will change with space-time diagrams is that time and position are placed on an equal footing. And traditionally, although we don't have to, but traditionally, we plot time on the y-axis. So again, if you want to think of space-time diagrams like motion graphs, that's great. Let me demonstrate an example of use of space-time diagram. Let me sketch a picture first. Let's say we have a train that's moving in the positive x direction at some speed v. And we'll say this v is comparable to speed of light c. We have the train station, and everything is set up so that at time equals 0, the train's back end is at x equals 0. We can illustrate this setup on the space-time diagram this way. Let me call the back of the train 1 and the front of the train 2. Then this point can be illustrated on the space-time diagram 1 and 2. And we also have a point at the station. This point on the station here, let me call that 3. And let's just pick a point on the station that matches the front of the train at this moment in time. Let me call that 4. On this space-time diagram, we can illustrate the trajectory of these points. These are set of space and time coordinates occupied this particular body at all times. So starting from time equals 0, I could diagram these set of points that are occupied by the back of the train. Again, as a reminder, the train is moving at a relativistic speed. And the front of the train follows a similar line. We call these lines world lines. I guess we give it a different name than trajectory because usually when you think about trajectory, you are thinking of a path traced out by an object in space, and often we forget about the time information. But on space-time diagram, the time information is very important. In fact, we have chosen to illustrate only one dimension, x, so that we can diagram the time dimension on our two-dimensional plane. We can draw similar world lines for the station points as well. And when we do, you will see that they are just vertical lines. So what this diagram illustrates is the fact that points 3 and 4 remain where they are in the, I guess I should have said that this is the reference frame of the station. And in the station frame, these 2 points remain at rest. They remain at the same point for all time. And this extends to negative time as well. And the points on the train, they change as time passes. So at some later time, you see that the position coordinates of both 1 and 2 are more positive than they were before. And using these space-time diagrams, it is possible to describe more complicated interactions. So, for example, in the case of motion graphs, I could plot the position of the incoming object and the position of the stationary object. And when you plot them both, as they collide, you see something interesting. Something that I think we are already familiar with. And I set up the parameters of these objects so that they wouldn't bounce from each other. You can imagine these two plots being superimposed to each other and how the position of the stationary block was something like here, horizontal line, until it collided, and then they are moving together. So we could do all that, and there may be situations where it's useful to do that with a space-time diagram. But in most application of space-time diagram you will see in this class, you will see straight lines or lines that I can draw as straight as possible. Okay, so that's enough of an introduction. The real utility of space-time diagram comes in illustration of Lorentz transformation and consequences of Lorentz transformation. So let me first remind you what Lorentz transformation is. It describes how time and space coordinates change with the change of inertial reference frame. I'm going to use two very common variables that are used to write down Lorentz transformation. One is speed as a unit of speed of light. So whenever I write down beta, it means v over c. So I'm writing down speed as a fraction of speed of light. And the other is the Lorentz factor, gamma, which I will write in terms of beta. So it's 1 over square root of 1 minus beta squared. With these two parameters, we can write down Lorentz transformation very compactly. Ct prime is equal to gamma Ct minus beta x. X prime is equal to gamma x minus beta Ct. In this particular case where the motion is only along the x direction, y and z coordinates do not change. Let me try describing here one other reference frame that can be related to the station frame. Let me color code this a little bit better so that I can separate things out. Okay, now everything associated with the station frame is in black color, and I'm going to attach a new coordinate axis to this back of the train, and that'll define my new x prime axis, which is at 0 at the back of the train. Now, as you look at all these points that represents the location of the back of the train, I hope you notice that all those points have value of x prime equal to 0. And those are the set of points that'll define my new Ct prime axis. Please take a moment to think this through. The Ct axis was the set of points where the coordinate x was 0 for all time. And in a similar way, the Ct prime axis is the set of points where coordinate x prime is equal to 0. Okay, that's simple enough. Now, my coordinate axis has a time and space coordinates. So, what do you think the x prime axis will look like? Here's one consideration that can help us specify the new x prime axis. We can look at the x-axis. When you look at the points that make up the x-axis, all these are points where time coordinate Ct is equal to 0. So if we can find the set of points where the time coordinate ct prime is equal to 0, we'll have found the x prime axis. Now, before you go thinking, aren't these two the same? Let me caution you that you should take a look at the Lorentz transformation. At x equals 0, sure, if t is equal to 0, t prime will be equal to 0. But at any other value of x, t being 0 doesn't mean that t prime is equal to 0. So let's go through a quick mathematical derivation here. I want to find a set of points where ct prime is equal to 0. So let me take this expression here and set it equal to 0. I can divide both sides by gamma to cancel that out. Then I have ct minus beta x is equal to 0. Let me solve this for ct, since my graph is ct along the y-axis. So ct is equal to beta x. This is an equation that defines a line on this graph. It basically says y is equal to beta x. It's describing a line with a slope beta. I think it's easier to see what that looks like if I first draw a line with a slope 1. That would represent the world line of something that's moving at the speed of light. So this dotted line represents how quickly light moves, and beta, being a fraction of speed of light, it'll be less than that. So for the line represented by ct equals beta x, I need to draw a line that's lower. And in fact, if you consider what the world line of the back of the train represents, the set of points defined by this expression will look like this. It kind of looks symmetric. The slope of x prime axis is beta, and the slope of ct prime axis is 1 over beta. And graphically, these two angles end up being the same. Okay, I'll save that for the geometry of space-time lecture. So now these green axes that I've drawn, they represent the train frame. There is an already interesting feature to point out that I think you can see from a careful consideration of the drawing that I have already drawn. So think back to how we describe the points 1, 2, 3, and 4. Now, we can talk about space-time event. Event is simply a term that we use to describe a particular point. For example, this one in our space-time diagram. So you could call this the event of the front of the train crossing, this point labeled as number 4 on the station. Now, this event happens at t equals 0. That's how we defined it. And this crossing event happened at the same time as the crossing of the back of the train with the point 3. Now, I want you to consider that same event in the train frame. In the train frame, the back of the train still crossed point 3 at t prime equals 0. That's how it was set up. And now, all the set of points that have t prime equal to 0 are these axis points, which means this event of number 2 crossing number 4, that didn't happen at ct prime equals 0. In fact, considering the arrangement, it looks like it happened for some time value less than 0. So in the train frame, the front of the train crosses this point before the back of the train does. If this sounds weird to you, I want you to think back to when we said simultaneity is relative.
That is what this space-time diagram is illustrating. That these two events, which happened simultaneously in the station frame, they do not occur simultaneously in the train frame. Okay, let me wrap up with two more examples. Okay, let me move some of the things around so that I have this space for drawing for my examples. So this first example is the same situation that we used to introduce the relativity of simultaneity. So let's say that we have a light bulb that's placed in the middle of the train, and we pick a moment, let's say t equals 0, for this light bulb to go off. Then the light propagates in all directions at speed c. And we gave a description of that before without use of space-time diagram. So this time, let's give that description with the use of space-time diagram. This is the space-time event where the light bulb goes off. So I need to draw the world line of the light. There's the light that travels towards the front of the train. Note that I'm trying to draw it parallel to this light world line that I've drawn before. And there's the light that travels towards the back of the train. And this time I'm trying to draw it perpendicular to the light world line I've drawn before. And these are the events where the light reaches the back of the train, and the event where the light reaches the front of the train. And you can see here that these do not occur at the same time. And what's important to here is that these do not occur at the same time in the station frame. Their CT coordinates are different. Now, if I want to read off their train frame coordinate, their CT prime coordinate, these horizontal dotted lines I've drawn, I can't use those. Those dotted lines represent points where t is constant, not necessarily CT prime. To find the set of points where CT prime is constant, I need to find the points that are parallel to the x prime axis. So let me start from here and try to draw a line that's parallel to my x prime axis. It looks something like that. So these 2 points have the same CT prime coordinate. The arrival of the light at the front of the train and the back of the train, they occur simultaneously. Okay, let's wrap up with one more example, one that you haven't seen before. Let me get rid of the drawings for the example we just did. Let's try to get a pair of events that are simultaneous in the station frame. I think I can do it this way. I'm going to install light bulbs on the back of the train and on the front of the train. Now, these light bulbs are triggered in a special way. They will be triggered when they detect that this point of the train is crossing this point of the station for light number 1. And the light at the front of the train will be triggered when they detect that they are crossing this point of the station. I'm making use of the earlier setup that I have already made, which is that these 2 events happen simultaneously in the station frame. And as you will see when we look at some of the special relativity paradoxes later, this actually takes quite a bit of setting up. So for the moment, I won't go into that detailed setup, and just to say that this point number 4 has been specially chosen to ensure that the crossing here will happen simultaneously with the crossing of the back of the train. We did the multiple runs and just made sure that that happens. And we want to look at the light that comes from these 2 light bulbs from the perspective of 2 observers, Alice and Bob.
Alice is at the midpoint of the train. Bob is at the midpoint of the points number 3 and 4 on the train station. I can even draw the world lines of Alice and Bob. Alice would be at a midpoint of the train, somewhere here, traveling along a world line that's parallel to the front and the back of the train. Bob would be standing at the midpoint between points number 3 and 4 and stay there for all time. So his world line would look like a vertical line on our spacetime diagram. And the way it's set up, it should happen that the crossing of Alice's and Bob's world line also happens at time equals 0. That's the only way the setup makes sense. Okay, let me draw the world lines of light that emanate from point 1. Oh, that's just gonna be along this light world line that I've already drawn, and the light from 2. That should be perpendicular to the world line of light from 1. Now, this is what happens. Bob, who is traveling along this world line, sees both light from 1 and 2 arrive at him simultaneously, and will conclude that 1 and 2 occurred simultaneously. And indeed they did. They both happened at t equals 0, simultaneous, in the station frame. Now Alice, who is traveling along this world line, will see it differently. She sees the light from 2 before. That would be at this event here. And then at a later point, she sees light from 1. That would be this event here. So she concludes that the light from the front of the train flashed before the light from the back of the train did. And in fact, if you draw the line of simultaneity, line that is parallel to the x prime axis that goes through the point 2, this is below the x prime axis, meaning that the value of time here, or t prime value, is less than 0. The light bulb at the front of the train did flash before the light at the back of the train in the train frame. This example of relativity of simultaneity is the example that your textbook uses. And I hope you see how, with the use of space-time diagrams, these consequences of special relativity become much more clearly illustrated. And the value of a space-time diagram is really twofold. One is in when you learn how to correctly draw the Lorentz boosted axis, you are basically illustrating Lorentz transformation in a graphical form. And the second value is when we describe events and sequence of events in words, there's a tendency for people to assume simultaneity implicitly without explicitly saying so. The space-time diagram by geometric arrangement clearly illustrates when you have assumed some event to be simultaneous in a particular reference frame and when you didn't. And by explicitly incorporating this relativity of simultaneity, it helps us avoid conceptual errors. So that's everything I wanted to talk about with the space-time diagram, with the 2 examples that I hoped would illustrate its usefulness. And you will see this tool being used continuously as we work through applications of Lorentz transformation and especially the special relativity paradoxes.